Hello and welcome to the 15th Andrew Chamblin Memorial Lecture. My name is Harvey Rial and I'm a professor in the Department of Applied Mathematics and Theoretical Physics here at the University of Cambridge. Before I introduce our speaker, I'd like to start by saying a few words about Andrew Chamblin. So Andrew was born in Lubbock, Texas, and brought up in nearby Amarillo. After a brilliant undergraduate career at Rice University, he moved to the UK to study for a year in Oxford, where he worked on twistor theory with Roger Penrose. He then came here to Cambridge to study for a PhD under the supervision of Gary Gibbons and Stephen Hawking. He was subsequently elected to a junior research fellowship at Pembroke College, Cambridge, and held postdoctoral positions at several institutions before becoming an assistant professor at the University of Louisville in Kentucky. Andrew wrote many influential papers on general relativity and quantum gravity, including one which now has over 1,000 citations. Sadly, Andrew died unexpectedly in 2006 at the age of just 36. Following his death, his friends and family established this lecture series in his memory. The first Andrew Chamblin lecture was given by Stephen Hawking, and he was followed by many more very distinguished speakers. You can find recordings of many of the talks on our website. Now to today's talk. So let me start with a practical point. If you would like to ask the speaker a question, then we should have time to do that at the end of the talk, and you can do that using the Q&A function on Zoom. So we'll monitor these questions, and if there's time at the end, as I expect there will be, then we will ask the questions on your behalf. So now let me introduce our speaker. So Andrea Ghez earned her PhD from Caltech in 1992. And since 1994, she has been on the faculty at the University of California at Los Angeles, where she is Professor of Physics and Astronomy and holds the Loren B. Leichtman and Arthur E. Levine Chair in Astrophysics. She's best known for her work studying the center of our galaxy, which has led to the best evidence to date for the existence of supermassive black holes. She's received numerous honors and awards, most notably the Nobel Prize in Physics in 2020, which she shared with Reinhard Genzel and Roger Penrose. She's only the fourth woman to be awarded a Nobel Prize in Physics. An incomplete list of other prizes that she has been awarded includes the Crafoord Prize in Astronomy from the Royal Swedish Academy of Science, the Beckerian Medal from the Royal Society, a MacArthur Fellowship, and elections to the National Academy of Sciences, the American Academy of Arts and Sciences, and the American Philosophical Society. Andrea is committed to the communication of science to the general public and to inspiring girls into science. Andrea, I'm very pleased to welcome you to Cambridge, if only remotely. You can now share your screen and begin your talk when you are ready.
Thanks so much, Harvey. I'm really delighted to be giving this lecture. I only wish that I could be there in person. And in fact, the work that I'm going to share today was really in the early stage in terms of thinking about what was possible during a visit that I had right before I started my faculty job at UCLA at Cambridge. So I'm delighted to make that connection. This is work focused on the center of our galaxy, where the initial question was, is there a supermassive black hole at the center of our galaxy? And what I hope to explain to you or demonstrate to you in the next hour is that the answer is resoundingly yes. And this is giving us a wonderful opportunity to understand both the physics and astrophysics of black holes. This work started off with a very small team, and I really want to highlight the people involved, and in particular, the two on my left. This is a photo taken in the first year of this project. So this is Eric Becklin and Mark Morris, who have worked with me for the past 25 years. And so I'm very grateful for their intellectual contributions to this work. Also shown in this picture is my very first graduate student, Beth Klein. At this time, this project was a rather radical idea because it invoked a new way of using the Keck telescope. And there was such concern that this wouldn't work that the first proposal was actually turned down. And yet today, we've now not only continued this project for far longer than we had possibly imagined at the beginning, where we were only proposing a 3-year project. Today, we're still going strong 27 years later. So we've grown both in terms of the team. This is a picture that was taken just a few years ago at the summit of Mauna Kea, right outside of Keck Observatory. We have a core collaboration of roughly 27 people and a broader collaboration network of about 100. And now we are what one might call a key science case for the development of new technology on this facility and then the future 30-meter telescope. Two people I would like to highlight in addition to Mark and Eric in this photo are Jessica Liu and Tuan Do, who began as graduate students in the group and now are professors in their own right with their own grad students and postdocs participating in this project. So I really am very grateful for the opportunity to work with such a wonderful team and to have a team that's been coherent for the last 2 decades. Okay, so there's 2 big picture perspectives on why what we're doing might be an interesting thing to do. From a pure physics perspective, one wants to ask, do really massive black holes exist in the universe? These are some of the most exotic objects that we can think of. And then today, this question has migrated to the question of understanding how gravity works near a supermassive black hole. From an astronomy perspective, this work at the center of the galaxy is interesting because we have a unique opportunity to understand what the role that these massive black holes play in the formation and evolution of galaxies. And in fact, at the beginning or at the inception of this project, the way people would think about supermassive black holes, which we think reside at the center of galaxies, so 1 per galaxy, was there was a question of which came first, the black hole or the galaxy. It was sort of like the chicken or the egg question. And of course, we had ideas for how one or the other would form first and then cause the other. Today, we understand that this is most likely just an incorrect framework, because what we see is that the mass of these massive black holes at the center of galaxies seems to correlate with the mass of the central component of galaxies, suggesting that that these things form synergistically. In other words, whatever process forms the galaxy forms the black hole at the same time, and that there's some feedback mechanism that keeps this relationship between the mass of these 2 components in lockstep. So we also now at the center of the galaxy have an opportunity to look at the processes that might be at play to keep that connection as we see it. Okay, so let's back up even further. Since this is a general talk, it seems appropriate to ask, how do you observe something you can't see? Because of course, black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. So it seems appropriate to show a completely blank slide to define what a black hole is. So the way I'd like you to think about a black hole for this evening or this afternoon is to think of a black hole as an object whose mass is confined to 0 volume. So if we think about density, which is mass divided by volume, since the volume goes to 0, this means that density goes to infinity. And in physics, anytime you have a number going to infinity, it's known as a singularity, or it's effectively a giant red arrow that says you don't have the description of the physical world correct here. Okay, so for that reason, black holes are incredibly compelling because they represent the breakdown of our understanding of physics and introduce an opportunity to further our understanding. And in particular, the breakdown appears to come from our inability to bring together two fundamental fields of physics, the fields of quantum mechanics, which is the description of things that are very small. And of course, an object with no finite size is incredibly small, the smallest thing you can describe. And then the field of general relativity, which is what Einstein is so famous for. So the study of regions of space where gravity is very strong. Okay, so that's the hope of understanding black holes, is to figure out how to make these two fields come together. And presumably when that happens, we'll be able to really describe what a black hole is. For this work, though, we can set aside this very major problem because there is a size that we can associate with a black hole. It's not the physical size of the black hole, but rather an abstract radius that's the last point at which light can escape from the black hole. It's known as the Schwarzschild radius, after the person who understood the meaning of this scale. It's also known as the event horizon, has been popularized by Star Trek. So you can't, if you're on the outside of this scale, you can't communicate with what's inside. So that's an interesting dilemma. But it's also important because while every object has a Schwarzschild radius associated with it, at this radius, if you can confine the mass to its Schwarzschild radius, gravity overcomes all other known forces and forces the object to become the infinitesimally small object of a black hole. In other words, this is the point at which gravity wins. If we look at different objects, we can see what happens. So if we could take the Earth and squeeze it down to the scale of a sugar cube, it would become a black hole. In other words, at this point, gravity wins. The Schwarzschild radius is actually incredibly simple to calculate because it scales directly with mass. You double the mass, you double the Schwarzschild radius. So if we were to take the sun and collapse it down to the scale of a university campus, here I've put UCLA, we could equivalently put Cambridge, it would become a black hole. So the most definitive evidence we could have for a black hole is to show that there's some mass inside its Schwarzschild radius. So that's really contains the key elements of the proof of a black hole. Now, where do black holes appear in the universe? There are two fundamental kinds of black holes that we talk about in astrophysics, and these two cases are actually a wonderful demonstration of the different modes in which science often proceeds. The first kind of black holes, what I'm going to call the stellar mass black holes, were thought of from a theoretical perspective. In other words, when people thought about what would happen to the most massive stars that are formed in our galaxy. These are stars that are roughly 30 times the mass of the sun. It was recognized that at the end of their lives, the outer layers of these stars would explode as a supernova, which is what we're looking at here. And there's all sorts of reasons that these supernova are important for the evolution of the universe. From the point of view of this talk, what's interesting is actually what happens on the smallest scales. And what happens on the smallest scales, the inside part of this of these massive stars collapse. The conditions are ripe for gravity overcoming all other known forces and forming what we call a stellar mass black hole. These black holes are roughly 10 times the mass of the sun. So they were thought of theoretically from the initially, and today we have beautiful observational evidence that these stellar mass black holes do indeed exist in the universe. There's been a huge evolution in our understanding, and the most definitive evidence today has come from the gravitational wave experiments from LIGO and Virgo. Now, what I'm interested in are the second case of black holes, what are known as the supermassive black holes. And as you might imagine, these are the ones that are much more massive. They're more like 1 million to 1 billion times the mass of the sun rather than 10 times the mass of the sun. And rather than theory leading, it was actually observations that led. And the idea from observations is that these supermassive black holes might reside at the center of galaxies. So this is a relatively famous image that was taken with Hubble Space Telescope and shows a number of galaxies. So every image or object that you see in this picture, except one, is a galaxy. So it's on a vastly different scale. Each galaxy, and we're going to focus in on this this galaxy on the top left, contains roughly 100 billion stars. So in the last picture, we were looking at one star. So the scale is really different. This picture that was taken at optical wavelengths, so wavelengths that are roughly what your eye detects, there's nothing actually that tells you that there might be a supermassive black hole at the center of these galaxies. It was observations taken at radio wavelengths, more or less where your cell phone works, that contained the first clue that there might be really massive black holes at the center of these galaxies. So at these wavelengths, what one sees is not starlight, but rather emission from gas. And there are two important phenomena here. One is that you see these enormous jets of emission coming out from the center of the galaxies. So these pictures or these galaxies are a small subset of all galaxies, roughly 10% of all galaxies. I like to call these the prima donnas of the galaxy world. They're sort of show-offs. They're called active galactic nuclei because their nuclei or centers are very active. So we think that at the center, there's some central engine that's powerful enough to drive these jets of emission or gas out from the center. The other thing that is notable about these galaxies is that at the core, there's emission or light that looks nothing like starlight, and in fact appears to be moving at very high speeds. So it's thought that this light is coming from matter falling through the event horizon onto the black holes. In other words, a popular way of thinking about this is that you're watching the dining habits of the supermassive black hole. Okay, so these kinds of observations led people to ask, do supermassive black holes exist in the universe to drive all this energetic phenomena that we see? That very quickly led, actually, Lyndon Bell and Rees, roughly half a century ago, to ask the question, do all galaxies harbor supermassive black holes at their centers? This is that spiral galaxy in the upper left corner of the Hubble Deep Field. And it's a galaxy that would look very much like our own if we could get outside it and look back. Now, we live roughly halfway out in our own galaxy. And what we're looking for is a black hole at the center. And almost every way you can describe a galaxy, things become more intense or more extreme as you head towards the center of the galaxy. So not only are we looking for a supermassive black hole in this region, but the astrophysical environment becomes very rich to look at. So a couple of ways that we can talk about is that the density of stars goes up. So if you think about actually human populations, you can think of this as like the downtown crowded urban hub, maybe like New York City or London, whereas we're out in the suburbs. So the density of stars is roughly 1 billion times higher in this region than where we are. And of course, everything moves very quickly in this region. And almost any other way that you can describe the galaxy is more extreme. So there's lots of interesting astrophysics in this region. Now we want to look at the center of the galaxy, and we definitely have the pro of the center of our own galaxy being the closest example of the center of the galaxy that we'll ever have to study. The next closest galaxy is 100 times further away. So that's the pro. But the con is that we live within our own galaxy. So galaxies are flattened disk-like structures. So in order to see the center of the galaxy, you have to look through the plane of the galaxy. And this photograph very nicely shows some of the challenges associated with that perspective. So this is taken on in Hawaii. It's actually where the telescopes are. and you see the plane of the galaxy through the swath of light that's observable. But you can also see that there's a lack of light running through the plane, and that lack of light comes from dust that also resides in the plane of the galaxy. I'm from Los Angeles. I have a very good appreciation for what dust in the atmosphere does. Dust is very good at blocking light, in particular light that's roughly has a wavelength that's roughly the scale of the dust particles. So in the optical, where your eye detects it, only 1 out of every 10 billion photons or light packets makes it from the center of the galaxy to us. So it's basically invisible. But if you go to the infrared, and in particular where this work is done, is mostly at about 2 microns. So the infrared is roughly where, oops, my apologies, where your TV remote control works. Okay, so infrared is essential here. So one of the keys to why this experiment is possible today is the tremendous progress that's been made in the development of infrared technology. And that, in fact, that's associated with UCLA's decision to go into infrared astronomy, because UCLA is located in Los Angeles, where there's a very rich community of aerospace industries that also care about the development of infrared detectors. Sorry, I don't know what's going on. So let's see. As we go to the center of the galaxy, what we're interested in is finding the stars that are as close to the center of the galaxy as possible to study or to see how stars move under the gravitational influence of the central black hole. So these stars move for the same reason that the planets orbit the sun, because of the gravitational influence of what's at the center of their orbit. So from these, if you can find these stars, then they will tell you through the measurement of the orbit how much mass is inside their orbit. And then, of course, the shape of the orbit tells you the scale that you can find the mass to. So in this effort to find a black hole, what you really want to be able to do is to find the stars that are as close to the heart of the galaxy as possible. And this tells you why actually the working at the Keck Observatory was so important to this work. So big telescopes, so Keck Observatory is the largest telescope in the world. And the way we characterize big telescopes is by the diameter of the primary mirror. So 10 meters is the diameter of this telescope, and that's like the width of a tennis court. There are 2 promises of large telescopes. One is that you should be able to see things that are very faint, because you can treat it like effectively, or think of it as effectively like a light bucket. And then the second promise is that you can see very fine details. So you can get to very high angular resolution. And the analogy I like to make here is that if you think about the painting technique of pointillism, where you paint with individual dots, as you move closer or walk closer to the painting, your ability to see the individual dots improves. So having a large telescope in principle is like you're improving your ability to see those individual dots in the universe. Now, okay, so those are the 2 promises. These telescopes are located in Hawaii. The reason that they're located in Hawaii is because there's a number of things that are satisfied that makes Hawaii be one of the best places to put big telescopes in the world. One is that you're above most of the atmosphere, so there's very little atmosphere to look through. 2 is that you're in the middle of an ocean. And not only do you want to minimize the atmosphere that you have to look through, but you want that atmospheric flow, the flow that goes over the telescope, to be very calm. So big bodies of water stabilize the atmospheric flow, so it keeps it the turbulence down. So big telescopes tend to be on high peaks near large bodies of water. So in Hawaii, in the Chilean Andes, in the Canaries, and those are the two properties that are essential for that choice. There's a third property, which is that astronomers don't like contaminating light. So you want to find a part of the world that won't be affected by regions of the world that are highly developed. And that's an interesting challenge, because while you want the light pollution to be low, you also want to be able to have access to high-tech industries. And those two criteria are actually in tension with one another. So Hawaii actually has, in the past, been very good about putting in ordinances to keep the light pollution low. So there are about a dozen telescopes from all around the world. Of course, the United Kingdom has telescopes that have been up here and that are up here, along with many other countries around the world. Okay, so let's think about the objective of getting to the highest resolution possible. And one of the challenges to this is the atmosphere, which is great for us. It allows us to survive here on Earth, but it is a total headache for getting clear and sharp pictures of the universe. So if you think about the light that's been traveling from the center of the galaxy, which departed the center of the galaxy 26,000 years, in the last 30 microseconds, it hits the top of the atmosphere and gets distorted. Okay, so while these telescopes are on a high peak up at 14,000 feet, or roughly 4,000 meters, gets through a lot of the atmosphere, there's still some remaining atmosphere there. This is actually some of the earliest data that we took at the center of the galaxy. We today know that where the black hole is roughly in the middle of this picture, but you can see the light from 5 of the brightest stars, and these stars are suffering the distorting effects of the Earth's atmosphere. So you can see that the way they're getting distributed, the light is getting distributed, is the same for every star. If there was no atmosphere here, each star would be the size of the smallest structures dancing around and rock solid still. Okay, so astronomers and astrophysicists have worked very hard on ways of overcoming this problem, and this is one of the things that I've focused on for much of my career. One solution, of course, is to put a telescope above the atmosphere. This is the solution of Hubble Space Telescope, as well as the solution of James Webb Space Telescope, which will be launched next month. But both of these telescopes have a mirror diameter that's much smaller than what we have here on the ground with the Keck telescope. So the Keck is 10 meters. This picture is of Hubble, which is 2.4 meters. And of course, the James Webb is 6 meters. And the advantage of diameter, the scientific power for this experiment, goes as the diameter of your mirror to the 4th power. So this improvement is actually a very significant improvement, since compared to Hubble, it's a factor of 4 to the 4th power. You're getting to roughly factors of 100. Okay, so there are a lot of ways of beating the atmosphere from the ground with Keck, and this animation shows the benefit of doing so. So the 5 bright stars that I was showing you before are here, and if you take a long exposure, you get these big blobs. This is what's called a direct image, and if you carry out some correction. And that technique has actually changed or evolved a lot over the last 2 decades. So what we've done has really improved dramatically, and I'll share a bit with you in a moment. But the point I wanted to make here is that the stars that we want to A, discover, and then 2, track in order to prove that there's a black hole, and to understand, and then to further understand the physics and astrophysics of black holes, are located in the middle of this box. And you can see without these techniques, you can't even see them. You need to track thousands of stars in order to properly register all these frames. So while these are the sort of what you might call the stars of the show, there's many other stars that you need to measure in order to understand the absolute motion of the stars. All right, this is supposed to remind me to say that in the early days, we did something that was hardware simple, but computationally complex. Okay, so one of the things I've really appreciated about working at the Keck Observatory, which is co-owned by the University of California and Caltech, is that faculty are allowed or permitted to propose to both build instruments and modify instruments that already exist. So this initial experiment, which was simple, hardware simple, all we needed to do is to take the existing instrument and modify the optics so that you could get to a smaller pixel scale, and modify the electronics such that you could take really quick, short exposures to keep up with the distorting effects of the Earth's atmosphere. Okay, so that was a relatively straightforward fix. And then you take all these short exposures back, and you do a lot of number crunching to try to figure out what the underlying object function is compared to how it's been distorted by the atmosphere. So there's a lot of thinking about deconvolution methods. On the these are the short exposures. On the right is the final image in the early days. I mean, these are really early day images. So back 20 years ago, we were so excited to see these, and today they look pretty primitive. Nonetheless, you can see the stars that matter. And in this animation, I'm showing you one image per year. And the reason I like to show this is this is really the data. There's no cleaning up, making it pretty. So you can see that there are stars, and you can probably find my favorite star in the entire universe, or certainly in our galaxy. Its name is SO2. And you don't need any fancy algorithms to tell you that there's something really interesting happening at the center of the galaxy. And of course, I could look at this animation for a very, very, very long time, just recalling that that first review basically told us that where we didn't get telescope time, and the review basically said our techniques wouldn't work, we wouldn't see stars, and we wouldn't see them move. And so it's incredibly gratifying to have been able to make these animations and see basically for the whole thing to have worked. But we've gone so much further than what we had imagined in those early days because the technology has advanced so much further. So while we were doing these early techniques, which are called speckle imaging, what was being developed in parallel was a technique called adaptive optics. And this adaptive optics is a wonderful demonstration of the benefit of technology transfer between multiple fields. So it turns out not only is the astronomy community interested in seeing through the atmosphere, but also the military community is very interested and generally has much more money than the scientific community. So as the astronomers were making progress with developing these techniques, this business was declassified in the early 90s, sharing that the military actually had working systems. So then it really became a matter of applying these techniques to an astrophysical setting. So this animation shows a little bit about how this technique works. We see a beam of light coming off the primary, bouncing off a secondary, going into the instrument bay. So that's what you've already seen. And now we're going to come into the adaptive optics instrument. And this is a schematic that really highlights some of the key elements. And in particular, I want to highlight the optical element that's in the top right here. This is known as the deformable mirror. So this is the mirror where all the action is it takes place. So the goal is to have this mirror take the conjugate shape to what the atmosphere has imposed on your light. So now we're seeing a new depiction of the light, no longer a beam of light, which shows the direction of light, but the wavefront. Because of the atmosphere, these look like Pringles potato chips. They should be, and then once it bounces off the deformable mirror, it looks like a flat pancake. In other words, you've removed, in principle, the distorting effects of the Earth's atmosphere. So there's all sorts of interesting technical challenges associated with adaptive optics systems, ranging from hardware questions about how do you build a mirror that can accurately move on such short time scales and on such small scales, as well as computational issues associated with doing the computations that are quickly enough to feed back to that deformable mirror. And in all of this, you also have to look at something that's bright enough to allow you to make those corrections. And so today, what's really made this a scientifically productive approach is the use of lasers, which generate artificial stars because of a fluke of nature. So up at 90 kilometers, there's a thin layer of sodium atoms that are deposited by meteors and are trapped in a layer that is about 4 kilometers thick. So we shine lasers that stimulate those sodium atoms to shine, and creating a star that's bright enough for us to observe and provide the information that we can move that deformable mirror and make the corrections. This is amazing. This is really a remarkable technology, and it's really advanced what can be done scientifically. I mean, not only can we take images that are a factor of 10 better than in any way you could describe it, but also you can take images at different wavelengths, and you can take spectra, and spectra really are so important in the work of astronomy and astrophysics. It both gives you the third dimension of motion. So here I'm now focusing on stars that are on a much smaller scale than even that small box I was showing you before. This is now a fourth of the real estate. So the star that I highlighted that it was moving very quickly, that's SO2, it's shown here. So now we have both the 2 dimensions of motion on the plane of the sky, and with the spectra, we can get the third dimension of the motion along our line of sight by looking for shifts in the wavelengths of light. So this is the Doppler effect. Okay, so what does SO2 tell us, and what has it already told us, and what does it have the potential to tell us going forward? So what it has already told us is that the 4 million times the mass of the sun that we recognized 30 years ago to be within this giant circle. So this is sort of the starting place for the work, and this giant circle is so much larger than the Schwarzschild radius. There were really no claims that this was a supermassive black hole at the time. But what this work has done has to confine that mass to a volume that's 10 million times smaller than what we knew at the outset. In other words, we've advanced our understanding or the evidence for the existence of supermassive black holes by a factor of 10 million. So we now have 4 million times the mass of the sun within the scale that corresponds to the size of our solar system. So this was a huge step forward. The original vision for this project, which we proposed at the beginning, which was 3 years, brought us the first factor of 1,000. Where the goal was only to measure the statistical properties of the stars, and then the breakthrough of measuring complete orbits brought us the next factor of 10,000. So this has really been an amazing transformation in our understanding for the existence of supermassive black hole, not only in our own galaxy, but in any galaxy that exists in the universe. And really, this is what's being recognized with the Nobel Prize. I really wish I had a picture with all 3 of us, but because of the pandemic, there was no in-person ceremony. So this is actually showing from the Crawford Prize. I wanted to show this because I really wanted to recognize that there have been 2 groups at this from an observational perspective for the last 2, actually, and today, almost 3 decades. And that it's been tremendously helpful to have these 2 groups from my perspective, because there's nothing like competition to keep you on your toes. and to really have the diversity of thinking about how you make these measurements that are actually quite hard. So I think both groups we've pushed each other's, and I think we've gotten to much better science for the existence of the two teams. Now the two teams are continuing this work, and the questions have moved to a different arena, which is it's no longer about proving the existence of a supermassive black hole, but rather understanding both the physics and the astrophysics. So let me spend a few minutes talking about what we've learned from a astrophysical role. And in this arena where we'd like to understand the relationship between the black hole and its host galaxy, has been one of the most delightful aspects of working with new technology. New technology which allows us to see the universe in a way that we couldn't before, in this case, has shown that almost every prediction that we could make for what we should see in the environment around the black hole is actually inconsistent with the prediction. So in other words, I think I've said that backwards, but in other words, the predictions, the observations are inconsistent with the predictions. And of course, from a point of view of a scientist, this is like being a kid in the candy shop. There's so much more for us to do and understand. So let me give you a little bit of a sense of some of the things that we've been thinking about. Actually, I'm just going to go straight to this animation. In this animation, I'm color coding the kinds of stars that we see. And it's only with the advent of adaptive optics in which you get to measure the spectra, which tell us what kind of stars we're seeing. There are three categories of objects that I've coded here. So the first one that I'd like to highlight are the young stars. The young stars are the green stars, the aqua green stars. And young stars, the prediction is simply that you shouldn't see young stars near a supermassive black hole. And in fact, young stars at even greater distances were the reason people, one of the reasons that people put forward for not believing in the existence of a supermassive black hole. Okay, so young stars form from large clouds of gas and dust, which are very fragile. In order to form a star, that cloud needs to collapse under its own self-gravity. If you put that cloud near a supermassive black hole, the gravitational forces will be much larger on one side of the object than the other, and will distort or tear that cloud apart. So that's the reason that we didn't expect young stars. The densities of gas that you need to overcome those tidal forces are 10 to the 8th times higher, so 100 million times higher than what's observed today. So this has created the problem of the paradox of youth, because they're clearly there. And the fact that today, as we move out to larger radii than the stars that I've been focusing on at the beginning of this lecture, many of those stars seem to reside in a disk, points the way to a possible explanation that perhaps our galaxy had a disk of gas, very much like the active galactic nuclei, out of which these stars form, suggesting that our galaxy was much more active in the past than it is today. So that's paradox number one. I think one of there are actually many other suggestions for the solution. And one of the challenges to this current thinking is that only 20% of the young stars appear to reside in the disk. So in other words, how do you get 80% out of the disk? So that's the challenge for today. The other prediction is the orange stars. The orange stars are the old stars, and old stars have had a lot of time to form elsewhere, and through interactions are expected to congregate around the most massive object in the system, which is the supermassive black hole. So you expect an entourage, a clustering, or in fact, as we say in an excess density around the black hole, which is known as a cusp. And yet there are very few old stars in this animation, or that we can see today. So there's a dearth of old stars when you expect an overabundance. And in fact, this overabundance is how we try to infer the presence of supermassive black holes in other galaxies. So this contradiction has important implications elsewhere. The third category of questions that has arisen, and we're not that I want to highlight, because there's certainly many more, are the magenta stars, the pink stars here. These are objects where we actually see evidence that these stars' outer layers are being torn off as they make their closest approach to the black hole. And so this is rather amazing. You can actually start by seeing an object that's compact, see it come in, get extended, and then become compact again. And again, think about the scales and the distances that we're observing, and to be able to see something like that on a human timescale is rather amazing. The reason this is so surprising is that on these at these scales, to get those kinds of interactions to happen, one needs a star that's 100 times larger than any kind of star that we predicted to exist at the center of the galaxy. And here, one of my favorite scenarios for explaining this mystery, although by no means is unique, this is the most recent of the three mysteries, is the idea that the black hole has driven pairs of stars, binary stars, to merge. And it turns out that most stars are formed as binary stars. So in fact, the idea that a binary star might live near a supermassive black hole isn't so crazy. And that when stars merge, they become bloated. In fact, they inflate. It's almost like resetting the clock to look like what's known as protostars. And so that allows us, or creates an object that would have the scale to experience this kind of interaction. The lovely thing about this scenario, or this idea, is that this might be highlighting a process that's important for understanding some of the mysteries that have been seen with the gravitational wave experiment. So if you'd asked me roughly, let's see, 5 to 10 years ago, whether or not there was a connection between this work in general and the gravitational wave experiment, I would have said no. But what this is suggesting, this dynamical interaction between the supermassive black hole and binaries, is a process that may be leading to some of the, a pathway for understanding the gravitational wave merger events, which are happening more often than originally predicted, and from objects that are larger than expected, that this merger hypothesis might give an important pathway for thinking about those objects as well. Okay, let me just end with a little bit of our work on testing gravitational, how gravity works. So I don't know, roughly right when we started measuring orbits, it became clear that the orbits of these stars would give us a unique ability to test general relativity in a regime that had never been tested before. In other words, an opportunity to ask how gravity works in this extreme environment. And there are a couple of different tests that are possible, but the key here is that you have to have stars that you've measured complete orbits for. In other words, that you've seen these objects go all the way around in order to get a seat at the table to make these tests. You can look at both how the light is affected, which is looking for what's known as the gravitational redshift. And that was possible when the star SO2 had made a complete orbit. And then the first time it makes its closest approach after the complete orbit, you have an opportunity to look at the energy that's been lost by these photons as they climb out of the gravitational potential well and make their way from the star itself to the telescope. The second test that we're on the way to looking at is the motion of the object itself as it moves through space and time that have become coupled thanks to the presence of a supermassive black hole. I think what I would like to leave you with is the two things. One is that this first test seems to conform to what we expected. And this second test has much more controversy associated with it. This is a test that is best measured at apoapse, in other words, the furthest approach. That furthest approach will happen in 2026. So this is a signal that's emerging as we go from closest approach in 2018 to the furthest approach. And our early results actually show that the object seems to be moving or precessing in a direction that's opposite what was expected from gravity. And that's a super interesting result because that could occur with the presence of dark matter. So I love this. Again, I like these. For me, it's the most exciting phase when you see things that you don't expect, because it really forces you to ask in detail, have you made a discovery, or have you just discovered some weakness in your analysis? And it's important to recognize that to make these measurements, you have to put 3 decades of measurements together in a coherent manner without the accumulation of small errors. So we're in yet another interesting moment where we're effectively going around the car and kicking the tires to make sure that that our house is in order. From a technology perspective, we're also moving further ahead. All of this adaptive optics technology today is based on one laser, but because that sodium layer is up at a finite altitude and not infinitely far away like our stars, you can do even better with the corrections if you can launch multiple lasers. This is like doing a CAT scan on the atmosphere to make much better corrections. And I can say more about this if people are interested, but this is a really essential technological development if you want to go to the next generation of telescopes. Of course, there are 3 such telescopes that are being developed in the world today: the European Extremely Large Telescope, the Giant Magellan Telescope, and then the project that I'm involved with, which is the 30-meter International Observatory, which is shown here. As the name suggests, these telescopes are 3 times bigger than the current generation of telescopes. And again, since this the benefit goes as the diameter to the 4th power, once again, there's huge improvements that will be made with this next generation of facilities. I think it's important to recognize that what we see today is really just the tip of the iceberg. We see the brightest stars at the center of the galaxy. And in astrophysics, the brightest stars are the most infrequent stars. The density is lower. So we can't see the faint stars that are much more frequent and much more common because they blur together without getting to higher resolution. And the analogy that I like to make here is that it would be like trying to understand the stock market by only looking at the biggest transactions. They're infrequent, they're large, but you're missing the much more frequent, smaller scale interactions. So once we get to the scale of the 30-meter telescope, we'll be able to see a typical star like the sun, and we'll also be able to probe distances that are much closer. So with that, I'd like to close by saying, if nothing else, I hope I've convinced you that there's a supermassive black hole at the center of the galaxy, and that we have actually uncovered more questions than answers with the development of new technology. So if you'd like to learn more about what we do, check out the Galactic Center webpage, and I'm happy to take any questions. Thanks for your attention.
Okay, well, thank you very much, Andrea, for a very entertaining and educational talk. So just a reminder, if you'd like to ask a question to Andrea, then please type it in the Q&A. And I can see there are a few questions there already. So there are a couple of questions on a similar topic here. So first, let me combine them. So first question is, can you say a bit more about how you know the central black hole has a mass of 4 million times the mass of the sun? And then secondly, how do you get such a large mass into such a small space in the first place? In other words, how did the supermassive black hole get created?
So one of the things that's lovely about this experiment is that the physics that you need to describe why we think that there's 4 million times the mass of the sun is quite straightforward. So it really comes from Newton's laws or Kepler's laws, which all basically allow you, which help us describe the relationship between the orbital period, the size of the orbit or the semi-major axis, and the mass that is inside that orbit. So the mass is equal to that scale, the size, semi-major axis of the orbit cubed, divided by the period squared. So we measure the period. So SO2 has a period of 16 years. It goes around every 16 years. And the semi-major axis is on order of 1,000 astronomical units, which is the Earth-Sun distance. So about 10 times the scale of our, well, the closest approach is 100 AU, which is the size of the orbit. So that's how we know that there's 4 million times the mass of the sun. Let's see what the second question was. No, I've forgotten.
The second question was, how do supermassive black holes form in the first place?
Oh, right. Okay, so that is an interesting question and one that people are still pondering. But one of the dominant ideas is that these supermassive black holes are formed in the early universe when in concert with the formation of the galaxy itself. So in the early universe, the universe was incredibly simple, composed mostly just of hydrogen, and there were small density fluctuations that led to the collapse. So this is like a scaled up version of star formation, that if the density gets high enough, eventually self-gravity will overcome and allow that object to collapse. And in this case, on this scale, it's forming the galaxy. And at the heart of the galaxy, it forms something that ultimately becomes the supermassive black hole. So it's the concentration or the collapse from that early primordial goop.
Okay, a question from our colleague here in Cambridge, Hugh Osborne, who asks, why does the power of the telescope go as the fourth power?
It goes as the fourth power when you're in the confusion limited regime. In other words, when the halo of nearby stars dominates your noise. So you get a factor of d squared from the concentration of light, and then you get another factor of d squared from the reduction of the halos of other bright stars. So you get that kind of scaling when you talk about the detection of planets near nearby stars and in this confusion limited regime.
A question from me is, people talk about the great things you could do if you could find a pulsar orbiting the black hole at the galactic center. Can you say something about the possibility of detecting a pulsar and what you could do with it?
Oh yeah, I mean, we're living in a really exciting moment where there are a lot of different techniques that are being pursued to understand what's at the center of the galaxy. And pulsars are amazing probes in terms of these light beams that flash on short time scales. So people have long looked for the existence of a pulsar at the center of the galaxy. Now, I mentioned the dust that's between us and the center of the galaxy, but along with the dust, there's also a lot of gas, and that all that gas disperses the signal from pulsars, which has made it exceedingly difficult to find the pulsars. However, at this point, the techniques are getting better and better. So some people believe that there's actually an interesting, there may be a dearth of pulsars. So it's an interesting question. Is this, are we learning something about the center of the galaxy in which pulsars might not be produced in the way we expect? Or is it just a technical problem associated with the pulsar dispersion from all the gas between us and them? So that's where we are today. I think people are still thinking hard about this problem, both from a technical perspective and a theoretical perspective. What can we how might we understand the lack of pulsars in terms of the unusual environment?
Okay, so David Wiltshire asks, what are the ages and masses of the unexpected young stars discovered in orbit around the central black hole? And what does this tell us about the inner galactic disk?
Okay, so the scale, the age of these stars appears to be roughly 4 million times the mass. Sorry, what am I saying? I say 4 million and I automatically think about the mass. It's 4 million years. Okay, so these are pretty young stars. For the rest of the audience, if you anthropomorphize stars, the typical star at the center of the galaxy is 1 billion years. So these 4 million years is like the human gestation period. So these are really young stars. The structure at the center of the galaxy actually really looks like a scaled up solar system. So if you think about the ratio of the mass, I guess the other part of that question was what's the mass? These are pretty massive stars. So the brightest stars are Wolf-Rayet stars for the people who know about the names of how we label stars, but those stars are roughly 60 times the mass of the sun. And then we can see down to, for this kind of star, roughly down to 10 times the mass of the sun. So again, we're seeing really only the most massive, brightest part of the population. It actually was Doug Lynn who originally pointed this out to me. It's nice to think about this as a scaled up solar system. So he's somebody who thinks a lot about the solar system as well as the center of galaxies. So the ratio of a host star like the sun compared to planets, the surrounding planets, is the same as the supermassive black hole to these massive stars. So the gravitational dynamics that are at play may be very similar to what people think in terms of planet formation or planetary dynamics, which is incredibly helpful to recognize. So in terms of dynamicists who think about this problem, there's a lot of crossover between those two communities. In terms of the question about the inner disk, I mean, this is on the smallest scale. And one question that one might ask is, are you only seeing one small event that might be leading to the growth of the inner part of the galaxy? So in other words, are these young stars that we see today the result of some gas cloud that came in, dispersed, formed stars, and then as these stars evolve, blow away the material, and that what leads to the growth of the inner part of the galaxy is this happening repeatedly. There's absolutely no connection that we can figure out between the orientation of these disks, this inner disk, which is really small, and again, for the astronomers who think of in these units, the scale of this disk is roughly half a parsec. So it's a really small scale compared to the inner disk of the galaxy. Yeah, so it's not connected. I don't think I have anything else that's useful to say here on that front.
Okay, maybe a more general question. Someone asked, it was interesting to hear about trying to get your proposal accepted. And could you say a bit more about that? Was the engineering speculative, and how did you convince yourself it was going to work?
Oh yeah, I mean, I like to mention that, especially for the younger members of the audience, just because anything that's interesting, and it usually comes with huge hurdles along the way. So, science is a process of overcoming obstacles and trying things that don't work. I mean, that's almost the nature of the process. So I think it's useful to realize that things that seem obvious at the end of the day weren't obvious in the beginning. So it's okay. So let's think about why people might have been skeptical. So this was first proposed when Keck was first introduced. the architecture of Keck was radical. It's in itself. So before, people had built telescopes out of single, with mirrors, primary mirrors that were one chunk of glass. And so this was a departure. And in fact, there was long debates about whether or not this would work. So there's Keck is actually 36 hexagonal segments. And you have to align those segments to a fraction of the wavelength that you're observing at in order for those segments to act like a coherent mirror. So nobody had actually demonstrated yet that that had been achieved in order to, in a scientific experiment. So there was skepticism about whether or not the segments were what we called phased well enough. So that was, I think, one concern. I think this was probably the biggest concern. And that kind of technique, the speckle imaging, I had done a lot of. And what it was a reminder for me, how did I overcome this? Well, I was new faculty at UCLA. Nobody knew me, I was low man on the totem pole, so to speak. So the next year I went on a speaking tour up and down the University of California. Oh, I guess for those of you who don't know, the way time is allocated on these big facilities, for Keck at least, University of California has roughly half of the telescope time. So there's a committee of people who are composed of faculty across the University of California system. So I spent the next year going up and down the coast, giving talks and convincing the people who were on that committee or who might be on the committee in the following years that in fact this was possible. And then the other piece of this is that I was fortunate that I worked with somebody who was willing to demonstrate that this technique would work. In other words, just to try it out, not on the center of the galaxy, just to show, to do the proof of concept that you could actually get to the diffraction limit. And that was in 1994. And I have to say that was on one of the worst nights we've ever observed in. Like the seeing was horrendously bad. And I have to say, I had a moment of, oh my goodness, maybe this isn't going to work, but recognizing that we could make it work even in these awful conditions, helped overcome the skepticism that of what was really driving that the original question.
Okay, we have a question from an expert. Roman Rafikov is asking about a claim by Pasker et al., who said that the S62 star and some others come significantly closer to the black hole than S2, but this was put in question by the gravity results. And he's asking, what is your opinion on this controversy? Do we need TNT or ELT to resolve it, or can this?
I mean, there are quite a few stars in here, and their closest approaches are important. So not only are those stars potentially quite close, although you need to really understand their complete orbits to be sure. And one of the challenges. So I don't think I'm really concerned about. I mean, we've seen these stars; they're there, and I think the controversy might be what's the best probe of what's at the center, and what you'd ideally like is multiple probes. So this is all good news. So today we have roughly a dozen stars that have enough of an orbit that you can start to constrain the central potential in these more sophisticated ways. So in terms of the experiment that people are really excited about, which is the precession, looking at the precession of these stars, so SO2 being the clearest example, there are effectively three key effects that you want to control for. One is gravity, which is going to make things precess in a prograde sense. What's known as the dark cusp, or the existence of dark matter, is going to make things precess in the retrograde direction. And then the third is your reference frame. So this is a topic, and if you ask me what keeps me up at night in terms of making these measurements accurately, I would tell you it's the reference frame. 20 years ago, I would have told you this is probably one of the things I would think is boring. And today it's the thing I think is most interesting, because it's at the heart of understanding this precession, because you have to put everything in the same reference frame. And if your reference frame rotates, you've got a problem. And it turns out this is an incredibly hard problem, because everything in your field is moving. And not only is it moving, but it's moving under the gravitational influence of the black hole. So there are all sorts of simplifying assumptions that have been made over the last 2 decades by both groups, which were quite reasonable. But if you want to get into this precession business, you actually have to think about how those assumptions have actually broken down if you want to get into the precession business. So I think we're still in the early days. The more stars that you can measure, the better, because you really have to control for all 3 effects.
Okay, maybe one last question. So this is from Nathan, who says that you said that we see young bright stars in the galactic center. Are we also seeing old bright stars which could be close to their death?
Yes.
A step further, so I'll just finish the question. A step further, do we have a reason to believe that some massive stars have already died and left a stellar mass black hole in the galactic center?
So we definitely think that there should be a, there's actually 2 really important parts to that question. One is that we see the light from a population of stars that are old, that are roughly 1 billion years old. So these are the orange stars. These are red giants. So certainly evolved. And in fact, they're most likely evolved lower mass stars than the young stars that we're seeing here. There's definitely evidence of stars that have gone through supernova. So you can see supernova remnants in the region. So you know that there have been multiple generations of star formation, and that there should be an accumulation of neutron stars and black holes at the center. So in fact, one possible resolution to the lack of a cusp, or the concentration in the luminous stars, is that the cusp resides in the stellar remnant population. So in fact, the prediction for what that stellar remnant population should in fact create a precession that's detectable in the other direction and is roughly consistent with what we're seeing. So I think that's I mean, this is definitely where the debate resides today. So I think there's a lot more that will come out as we both are able to see a population that is fainter, and as these orbits allow us to dynamically probe what exists in this region.
Okay, well, thank you very much. So I think it's time to bring this event to a close now. So thank you very much for a very entertaining lecture. And thank you also for your patience in answering so many questions. So it's been really, really enjoyable. So thank you, Andrea.
It's been my pleasure.